Welcome, my dear student. We talk about the electrochemistry. Electrochemistry deals with the properties of a solution of electrolytes and with the process that occurs at the electrodes. Electrochemistry encompasses the study of electrical transport and the conversion of the electrical energy into a chemical energy and vice versa. The electrical transport takes place by means of electronic conductors and electrolytic conductors. In an electrolysis, the current is passed through the electrolyte solution. The system makes use of two types of the conductors of current, the electronic and the electrolytic conductors. The metal wire that join the supply to the electrodes are electronic conductors, and the electrolyte solution is a electrolytic conductor. The electronic conductor has electrons as the current carrier, whereas the electrolyte solution has ions as the current carriers. As the two types of ions are present in the solution, there will be two types of the current carriers. If we distinguished the electronic conductor and the electrolytic conductors, the conductors which the conductors of a current is carried by the movement of electrons. That is, the current is due to the movement of the electrons in case of electronic conductors, and the electrolytic conductors, the current is due to the flow or the movement of the ions. The flow of current is unidirectional in case of the electronic conductor. The flow or migration of ions takes place in both the direction in case of uh, electrolytic conductor. No chemical change takes place, only physical change occurs in an electronic conductor. Chemical change takes place, that is the electrolysis, it is due to the passage of the current in case of electrolyte conductor. It doesn't take involves transfer of matter in case of electronic conductor, and in an electrolyte conductor it involves the transfer of matter in the form of ions. The conductivity decreases with the increase in temperature for electronic conductor, and the electrolyte conductor, the conductivity increases with increase in temperature. Conductivity is generally high in case of electronic conductors. The conductivity is generally low as compared to the electronic conductor in electrolyte conductors. The metal in a solid state and molten state conduct a current in case of electronic conductor, and the molten electrolytes and their aqueous solutions conduct the current are electrolyte conductors. We study the various aspects of electrolyte conductance, the conductivity of electrolytes. The conductivity of a solution of an electrolyte is defined in terms of its resistance. The resistance of the solution of an electrolyte is measured by placing it between the two electrodes and using a principle of Wheatstone bridge circuit. The conductivity of a solution of electrolyte is measured in terms of resistance. Conductance of a solution is defined as a reciprocal of resistance and has unit as Siemens. It is written as S, and the conductance is presented as K. The electrolyte solution is taken in the conductivity cell and measures the conductance of the solution. The conductance of the solution depends on the volume of the solution that the two electrodes will enclose between them for the measurement of the conductance. The conductivity cell consists of a glass tube in which the two electrodes made up of the platinized platinum are enclosed such that the volume of the solution enclosed between them is about 1 centimeter cube. We consider the cell constant. The conductivity cell is a cell which encloses a volume of 1 cm cube. The conductance will depend on the geometry of the conductivity cell used for the measurement of the conductance. Cell constant is a term for the geometry of a conductivity cell. The conductance of the solution depends upon the area of each electrode small a and the distance between them is L. Thus, every conductivity cell has a cell constant. The cell constant is defined as the ratio of the distance of the separation between the two electrodes of the conductivity cell and the area of cross section of each electrode. The cell constant is equal to L upon A. L, it is in a centimeter, area it is in a centimeter square. Then the unit of cell constant is a centimeter inverse, or if we take the meter, then it is a meter inverse. In a laboratory, the cell constant is determined by using the K-cell solution of known concentration, that is 0.1 molar or 0.02 molar or 0.02 molar. The cell constant is equal to a specific conductance of 0.1 normal KCl upon the conductance of 0.1 normal KCl. Means the unit of specific conductance is the Siemens centimeter inverse divided by Siemens, then it is a centimeter inverse. The specific conductance is equal to cell constant into conductance. The specific conductance or the conductivity is a conductance of a solution per unit value. It has unit Siemens meter inverse or Siemens centimeter inverse or mho centimeter inverse. It is denoted by the Greek letter K, that is kappa. Kappa is equal to 1 upon rho, or it is equal to 1 upon small a into r. Kappa is a reciprocal of the specific resistance or the resistivity of an electrolyte solution. The kappa is a conductance of 1 centimeter cube of the electrolyte solution. The kappa is equal to 1 upon rho is equal to L upon A into R, means m meter divided by meter square into 1 upon S is equal to the Siemens meter inverse. If you take the centimeter inverse, then Siemens centimeter inverse. Then the concept that is the equivalent conductance, lambda EQ. It is defined as the conductance offered by that volume of a solution which contains one equivalent of electrolyte. One equivalent, that is we consider here 1 gram equivalent also. Conductance of all ions produced by 1 gram equivalent of an electrolyte in the solution, which is placed between the two parallel electrodes 1 centimeter apart. If 1 gram equivalent of electrolyte is dissolved in V centimeter cube of a solution, then lambda EQ is equal to K into V, where K is a specific conductance. The lambda EQ is equal to 1000 into K divided by N. K is a specific conductance, N is a normality of the solution. Here the unit of that is a Siemens, a centimeter square per equivalent, or Siemens centimeter square equivalent inverse. Here V is a volume of 1 centimeter cube containing 1 gram equivalent of an electrolyte, means a volume containing 1 gram equivalent, it is considered for the value V. Another term, that is the molar conductance, lambda m. M is lambda m molar conductance. It is defined as the conductance of the volume of the solution which contains 1 mole of the electrolyte. It's 1 gram mole of a electrolyte. The conductance of all the ions produced by 1 mole of electrolyte in the solution which is placed between two parallel electrodes 1 centimeter apart. Then lambda m is equal to 1000 K divided by M. K is the specific conductance, M is the molarity of a solution. Lambda m is equal to K into V. V is equal to the Consider here the V is 1000 divided by M. Lambda M is equal to K into V. Is equal to L divided by A into R into V. Means the unit is Siemens centimeter square mole inverse. The factors affecting the electrolyte solution. The aqueous solution or in a molten state, the electrolyte ionizes to form oppositely charged ions. The ions are free to move in the solution. The free movement of ions which are responsible for the conduction of the electricity. The important factors which affects or influences the free movement of the ions in the solution, that is the concentration of the electrolyte, nature of the electrolyte, interionic attractions, temperature, nature of a solvent. The concentration of electrolyte, if you consider the more the number of ions per unit volume, then higher is the conductance. Then nature of the electrolyte, if you consider the weakly ionized solution, the conductance is low, and in case of a strongly ionized solution, the conductance is high. Interionic interaction, if you consider the concentrated solution in which the forces of attraction between the charged ions is greater, hence the conductance is low. And the dilute solutions, the forces of attraction are negligible, and hence conductance is high. If you consider the temperature increases, the average kinetic energy of the ions in the solution increases. Therefore, the conductance of the solution also increases. The nature of the solvent. If you consider nature of the solvent, the viscosity of solvent affects the conductance. Greater the viscosity, the lower will be the mobility of the ions, and hence lower will be the conductance. Then another, that is the topic, that is the variation of equivalent conductance and the molar conductance with the concentration. The conductivity or the specific conductance is the conductance of a per unit volume of the solution. It is the conductance of 1 centimeter cube of electrolyte. When the electrolyte solution is diluted, the number of ions per unit value decreases. The number of ions present in the 1 cm cube of the solution decreases. Consequently, the specific conductance or the conductivity of the electrolyte solution also decreases as dilution increases, or there is a decrease in concentration. The electrolyte solution which have conductivity decreases. The variation of the molar or equivalent conductance with the concentration. The conductivity power of an electrolyte, it is due to the ions. The number of ions increases on a dilution, because the degree of dissociation of electrolyte solution increases on the dilution. The molar or the equivalent conductance increases as the number of ions present in the solution containing 1 gram equivalent or the 1 mole of the electrolyte increases with the dilution, or there is a decrease in concentration. This introduces the concept of limiting molar conductance or limiting equivalent conductance for the solution of an electrolyte. The limiting molar or equivalent conductance of a solution is that the value which will be approached as the concentration of the solution tends to 0. In terms of mathematical, it can be defined as the limit of molar or equivalent conductance as the concentration tends to 0. It will be a value that can be approached but cannot attain. It is denoted by the lambda 0 or the lambda infinity. The strong electrolytes are the salts, strong acids or bases that are totally dissociated at all concentrations. The strong electrolyte solutions produce a large number of ions even in dilute solutions. Hence, conductance of the strong electrolyte solution have a high value. The effect of a concentration on the molar conductance or equivalent conductance can be studied by plotting the lambda equivalent or lambda molarity against the square root of C. The plot is obtained, that is a straight line plot, and this R.G.Chougale developed a mathematical equation, that is a lambda EQ is equal to lambda EQ infinity minus small b square root of C. Small b is equal to A capital plus B capital lambda infinity. Lambda equivalent is a equilibrium constant, equivalent conductance at a given solution. Lambda EQ infinity is equal to equivalent conductance at infinite dilution. C is a concentration of solution, small b is a constant which depends on nature of the solvent and dielectric constant of the medium. A and B, these are the constant for the solvents. The water, methyl alcohol and ethyl alcohol are usually as a solvent in this study. The value of A and B for different solvents at different temperature. It is observed that the conductance values are high and increases slightly on dilution. Increase in conductance is linear with the dilution and reaches a maximum or the limiting value known as the equivalent conductance at infinite dilution or the zero concentration. And it is denoted by the lambda EQ infinity or lambda EQ 0 or the lambda molar m infinity or lambda m 0. The equivalent or molar conductance can be obtained by extrapolation of the curve to zero concentration or dilution approaches to infinity. The plot lambda m versus a square root of C shows that the at a higher it is molar conductance is higher at dilute solutions and the lower for the concentrated solution. In case of a concentrated solution, the density of ions is high, and due to the interionic attraction, the speed of the ions is reduced or decreased, lowering the value of the lambda m or lambda EQ. On increasing dilution, the ions move apart and interionic attractions are decreased. As a result, the value of equivalent or molar conductance increases. The molar conductance of a solution of strong electrolytes, for example KCl, HCl, varies linearly with the concentration. The limiting molar conductance of a strong electrolyte obtained as an intercept from the linear plot. Limiting, there is a lambda infinity or lambda 0. Weak electrolytes are the weak acids and bases that are partially dissociated even in dilute solutions. For example, acetic acid, aqueous solution of ammonia. The number of ions produced by weak electrolytes are very low. Few ions produced, hence the conductance values are very low. For example, for 0.1 molar solution of a weak electrolyte, the molar conductance value is of the order of 5 into 10 to minus 4 Siemens meter square mole inverse. For the same concentration, 0.1 molar value of conductance for strong electrolyte is 120 into 10 to minus 4 Siemens meter square mole inverse. A plot of lambda m against the lambda c for the weak electrolyte shows that in a concentrated solution, lambda m or lambda EQ values are low and it increases steadily with dilution. The lambda 0, that is a lambda EQ or lambda m, cannot be obtained by extrapolation method. When the concentration approaches 0, the graph becomes almost parallel to y-axis. The degree of dissociation is inversely proportional to the concentration. At higher concentration, the degree of dissociation is less. Therefore, lambda m or lambda EQ is less and vice versa. Thank you.